Welcome, everybody. Thanks for joining. You all came here because you're interested in the foundations of quantum mechanics. And this is a lecture series that will run over the course of this winter term in about 13 lectures, always Mondays at 6 p.m. Central European time, so that's time in Germany. My name is Florian Marquardt. And let's start right away. I want to announce, however, that this meeting is recorded so we can upload things afterwards to the course website. I will give the link to the course website in a moment. And also, at least today, I'm streaming it live on YouTube, even though I didn't announce it there. I just want to try out the technology, basically. So I hope everyone is okay with that. And so let's start right away. You come from all different places in the world, so I thought it's good to start to tell you where we are located. We are in Erlangen, that's a small university town in Bavaria in Germany. And so I myself, I'm a scientist at the Max Planck Institute for the Science of Light. And as well, I'm a professor at the so-called Friedrich-Alexander-Universität Erlangen-Nürnberg in Germany. So as we go along, if you have any questions to ask, probably the easiest way to do so is to write something in the chat. The chat is right in front of me. Or else you could unmute yourself and also ask the question, whatever works best. But as long as you don't ask a question, it would be good if you mute yourself. Okay, so here's the menu, so to speak, of this course. What will we learn in this lecture series? We will start right away with one of the most fundamental discoveries in the foundations of quantum mechanics, and that is the so-called Bell inequalities. We will learn how they describe the consequences of correlations in quantum systems, correlations that are much, much stronger than you could deduce, not only from classical dynamics, but even, so to speak, from classical logic. These Bell inequalities are so fundamentally important because they are something like a no-go theorem. They rule out from the start a large set of possible theories that you could have hoped would somehow offer an underlying, more microscopic picture of what goes on in quantum systems. So they are extremely important. Their importance cannot be overstated. And that's why we learn about them right in the beginning of this lecture. Afterwards, we will deal with two aspects that are very tightly related, that is measurement and decoherence. What is shown here in the middle is basically a Stern-Gerlach apparatus where a magnetic field can deflect a particle according to its spin. And we will learn in this lecture series that this is only the first step in a chain of events that ultimately leads to a finished measurement where we can read something like a macroscopic result. Then we will discuss the issue of decoherence. That is actually very much related to measurement. They are basically two sides of the same coin. And in this context, we will also learn how one can describe the so-called quantum to classical crossover. So why is it that we don't easily observe quantum interference effects in macroscopic objects, like, for example, a cat being at the same time alive and dead? And then we move on to interpretations of quantum mechanics. So several attempts to make sense of what we see in quantum physics and to provide some explanations that would have the same observable consequences, but tell a different story about what's going on. And then finally, we will learn about possible extensions even of quantum mechanics. These go beyond quantum mechanics. They can produce predictions, observable predictions that would change what we now know And in principle, you could rule out those extensions if you do sufficiently careful experiments. So this is basically the menu of what we want to be discussing in this lecture series. I mentioned already there's a website. It's spelled out here, Foundations of Quantum Mechanics. On this website, you will find further links. So for example, you will find a link to a discussion group. It's some Google discussion group. It's free and open to everyone. You don't even need to register there. And I would suggest that we also use this discussion group to discuss about organizational details. For example, the local students at the Friedrich Alexander University, they need to know about the exam registration and so on. Let's defer that also to the discussion group as opposed to discussing it here during the lectures. And then you will find links to videos and slides and lecture notes. So right now there are already some links because in 2013 I was already giving this lecture, or actually in 2013 and 2016. So there are some original extended lecture notes and slides and videos available, but also as we go along in this version of the lecture series, which is more condensed and has new material, I will upload the video recordings. And then finally, we will also collect links to original articles. And whenever we have some exercises, there will be a few exercises throughout the course of this lecture series, then I will also put them up there. Okay, but now let's start for real. And I told you the menu of this lecture series, but what we want to start with first is a kind of introduction. And this introduction is a recap of the basics of quantum mechanics as you would learn about them in a first-year quantum mechanics course. This is first to bring everyone on the same page. We will not need very technical material anyway, but I want to recap the Schrödinger equation, for example. But then also we will go through it and look at it from a slightly different angle than you would usually do in a quantum mechanics first course, because we will already raise some of the questions that come up if you're a little bit skeptical. There's a first question. What about the background image used in the slide? Well, for me, this is a kind of representation of 0-point fluctuations of the electromagnetic field. But in reality, it's just a so-called Gaussian random noise field that you can generate by superimposing some random Fourier coefficients. Okay, so let's start. This is the Schrödinger equation, of course. And before I go on, I want to use this nice functionality that Zoom has, which is I can give you some questions. And so the first questions are purely for statistics, because I would like to know when, so at which year are you, or when did you start your undergraduate studies? When was your first year in university? And also which is the main subject that you are studying. So I will launch the poll now. I think you should all be able to see it now. Can someone confirm in the chat that you see the poll? Apparently some people are seeing the poll because some people are starting to answer. And yeah, I will wait until the answers have converged so I can get a feeling for the audience here. I see. So half of you are probably undergraduate and graduate students, and half, or slightly less than half, are a little bit more advanced. And the vast majority is studying or has studied physics and a few other fields, for example, engineering or chemistry. Okay, I think we have got all answers. And I think I can share the results with you. You should be able to see the answers, just in case you're interested. Okay, that's already very nice. And now, beyond the statistics, I'm also interested a little bit in your level of knowledge of quantum mechanics, but maybe the question I chose was a little bit too simple. So let me stop sharing here and move to the second poll. I have only a single question. You can read it yourself. What is the ground state of a particle in a box with infinitely high volts inside the box? Which function is it? Okay, answers are still coming in. The correct answer is in the majority, which is nice. And that's it, probably final 5 seconds. Okay, so this is the result. Fortunately, yes, the sine function is the correct answer, but a few of the other answers also got a little bit of results. Okay, so I was not asking about the details, of course, so it doesn't matter how exactly it is defined. Okay, so that's very nice. So now we can start. And you see, I want to do this a little bit live on my iPad, because I have a feeling that if we draw things step by step, we really get a better feeling of what's going on. So let's start the introduction, the recap, as I said. And that would be first the Schrödinger equation, just to remind everyone and bring everyone on the same page. Now, how did things start? Around 120 years ago already, people were very carefully studying heat radiation. So if you have an oven and there is heat trapped inside, then you have actually electromagnetic radiation of many different frequencies running around inside this box. And you can, for example, ask yourself, if I plot the intensity versus frequency, then which of the frequencies are predominant? And those who are a little bit further in their studies, they know that the result kind of looks like this. You start at very low intensity for low frequencies, go through a maximum, and then you go to very low intensities again. So this is the famous Planck spectrum of heat radiation. And actually what Max Planck had to do more than 100 years ago in order to be able to theoretically explain this, he had to make sure that especially at high frequencies, he gets the suppression of the heat radiation intensity correct. And the only way he found to make this happen was to assume that the energy in the electromagnetic radiation is quantized, as we would now say, so that, as it were, the heat radiation comes in energy packets of a size E equals h bar omega. So the larger the frequency, the larger these energy packets are. And so that's a result which is due to Planck in 1900. But for him, it was just more a mathematical formal device in order to get the right result that matched the experiment. And it was then Einstein who later took this mathematical result serious and really thought of photons as energy packets. So just to remind everyone, h bar is h divided by 2 pi. H is Planck's constant, and the value of this is 10 to the minus 34 joule seconds. So in other words, it's a very tiny number. Now, once you believe that the energy of the electromagnetic field comes in these energy packets, then you can start making for yourself a mental picture. For example, you can draw a wave packet, maybe it moves in this direction, and you can say, aha, the total energy inside this wave packet, that is h bar omega. And then you can go on and you ask yourself a different question. You ask, what's the momentum in this wave packet? And if for a moment you still adopt classical electromagnetism, if I tell you what's the energy, you can work out what's the total momentum, because there's the momentum density of the electromagnetic field. And if you integrate over that, over all of space, you will find that the energy and the momentum of this wave packet are related. The energy is just c times the velocity of light times the magnitude of the momentum. Now you see this immediately implies something very interesting. The energy is proportional to the frequency. On the other hand, the energy is also proportional to the momentum. And finally, we have for light, the frequency is the speed of light times the wave number k, where k, as you all remember, is 2 pi divided by the wavelength. So now suddenly we have a different relation coming up. Namely, if E equals h bar omega holds, then there must be an analogous relation between P and K. And so if I combine these equations, so I will immediately find P equals h bar K. Or if you want to have vectors, because the direction of motion is also specified, then it looks like this. So now this is a very interesting relation. And again, it's due to Einstein, because he took the concept of a photon series. If we wanted to describe things in a slightly more fancy way, then we could say relativity tells us that the energy and the momentum, they are not kind of independent, because if I change the frame of reference, then I know that both the energy and the momentum change, but they change in a very particular way. They change in such a way that actually they should be treated in the theory of special relativity as a 4-vector, with one component being the energy and another component, or another 3 components being the momentum. And for dimensional reasons, you multiply by the speed of light. Now, relativity also tells us that likewise, frequency and wave vector of a wave have to be combined into a 4-vector. So again, for dimensional reasons, it looks like this. And so you immediately see, if you postulate that there is a relation between E and omega, which we did with Planck and Einstein, then there must also be a relation between momentum and wave vector, because otherwise the relation between E and omega would break once you switch the frame of reference. Okay, so that's great. So that is true for photons. And the question is now, is it only true for photons? And that's where de Broglie comes in. Let me get another slide. Because he extended this concept to matter waves, for example, electrons. And what he assumed was simply that the same relation would hold. So E equals h bar omega and P equals h bar k. But the difference, of course, now would be that if you consider particles like electrons or atoms or molecules, material particles, then the relation between energy and momentum would change. So instead of E equals C times P, you would have rather something like E equals P squared over 2m, if we consider the non-relativistic law. In fact, de Broglie himself already tried the relativistic version, but for now, let's keep it simple. Now, once you accept this, then of course the question is, okay, now we know the relation between omega and k, and the question is, can we derive a wave equation that produces this relation. So we know h bar omega equals h bar squared k squared divided by 2m. So we have something that people would call a dispersion relation, omega as a function of k. For light, it is very simple. It's just a straight line. And now for these matter waves, it's no longer a straight line, but apparently a parabola. And so the question is, can we derive a wave equation? Now, in principle, there are many different kinds of wave equations. If you consider, for example, water waves and their amplitude is not very small, then these waves can be actually quite complicated. You arrive at a so-called nonlinear wave equation. So different waves, they can, if they collide, produce new waves of different frequencies and so on. So that's very difficult. But the simplest kind of wave equation is a linear wave equation. So if you don't know anything better, you start with the simplest possibility, and you want to derive a linear wave equation that would give you this dispersion relation. Now, if you are in free space, so what else do we know apart from the dispersion relation? Well, if we are in free space, and there is nothing around that would make one point of space or one point of time more special than others, then the solutions automatically must be plane waves. So as we would say, we have translational invariance, actually both in space and in time. And once you have a linear wave equation and you have translational invariance, then you can convince yourself very easily that the solutions must be plane waves. So the solutions must look like this, if you adopt the complex notation. And that is true even before you know the precise shape of the wave equation. And it would be true for water waves and pressure waves and sound waves in a solid and any other kind of wave you can imagine. Also, of course, for electromagnetic waves. So even here, it should be true. So that should be at least one permissible special solution to this wave equation, which we do not yet know. Okay. Now, if we have this hypothetical solution of our still unknown wave equation, of course, we can try how can we extract the frequency and the wave factor from this solution, because if we can do that, maybe we can play around with it and regroup terms so as to produce the correct wave equation. Well, if you want access to the frequency, for example, there's no better way to do this than to take the derivative with respect to time. Why is that? Well, because if I take the derivative with respect to time, then since it's an exponential, I just have to take the derivative of the exponent, and that will give me minus I omega, and then together with the prefactors, I get h bar omega times, and then the exponential function again. So the wave function reproduces itself, including any prefactor that I might have had. Okay, so that's great. So that's a way to get h bar omega, or as we call it, E. And then likewise, you can do the space derivative. And since that, according to my way of writing things, that occurs with a different sign in the exponent, you would also want to use a different sign here. And then you would find, aha, this is h bar k times psi. So now I wrote it in 1D. You can generalize this to higher dimensions. Okay, that's great because we know already this is the momentum. And so now I can immediately write down one linear wave equation that will have this as its solution. And I would just take the relation, basically I would take this relation up here between frequency and k and try to write it now in terms of these derivatives. So I would write on the left-hand side IH bar dt psi, and on the right-hand side I would write p squared over 2m, but we already know how to get a prefactor of the momentum. That's using this differential operator. If I want p squared, of course I square it, divide by 2m, and times psi. So now we bootstrapped ourselves, so to speak. It's a little bit funny. We, instead of starting with the equation and deriving its consequences, we started from the dispersion relation and some very general considerations like translational invariance. Then we guessed what must be the solution, and then we found the correct differential equation, the wave equation that would have this as a solution. So it's a little bit the other way around. So that's great. So this is an equation that will make sure that the solutions, well, are first of all of the plane wave type, and more importantly, that the omega and the k have the relation shown up here. So the question then is, of course, how do you proceed from there? In particular, to make it more interesting, what happens if you also have some potential energy? Because you want to have forces acting on this particle, so you need a potential energy. And there, it's a little bit more guesswork, shall we say, but it's not completely pure guesswork, because there are important constraints. For example, if you had the same potential all over space, it doesn't even depend on the position. That just means that you are shifting your zero of energy. And so the energy will then consist of both the kinetic energy written above, p squared over 2m, plus this constant value of the potential. And so in this case, obviously the equation should look like this. So you would have in total E psi equals p squared over 2m psi plus v psi. This is, so to speak, what you would need and what you would correctly get in this case. Now, the funny thing is that we can very easily generalize this to an arbitrary position-dependent potential. And the obvious generalization is if I make this potential simply position-dependent. So that's at least compatible for this case of, it's compatible first of all with this limiting case of a spatially homogeneous constant potential that we just discussed. It's also compatible with the general formula that you would have in classical mechanics, that energy equals p squared over 2m plus position-dependent potential. And it's also, we will comment on that later, keeps a certain integral conserved, namely the integral over psi squared over all of space. At the moment, so to speak, we don't yet know what this really means, but it's a very nice property to have. So, okay, so heuristically now we arrived at the Schrödinger equation. And at least, so at the time, of course, it was a major discovery, starting from these tentative ideas of de Broglie and coming up with a correct wave equation. But if nowadays you would find yourself in a similar situation, that someone tells you what's the dispersion relation, someone speculates, oh, maybe the wave equation should be linear and so on, it would more or less be an exercise in for a graduate student to figure out what is the correct equation behind it. Okay, so that was Schrödinger in 1926. And this is what we will be taking most of the time as the basis of our discussion. You also know probably, or hopefully, that there was an alternative formulation, which was even a little bit earlier, which was called at the time matrix mechanics, which is quite a bit more formal and abstract, but it was the first that was discovered, and that was due to Heisenberg just a year earlier. Actually, in 5 years, there will be the 100-year anniversary of that discovery. We will come back to Heisenberg, of course, later with the Heisenberg uncertainty relation, but we will have less to make use of this particular rather formal matrix mechanics. Okay, so that was just a side remark. Let's go on with the Schrödinger equation. Again, this is still our recap. When you have such a time-dependent wave equation, you can make an ansatz of so-called standing waves. So you can also do that for, say, pressure waves in a gas, or waves on a membrane that you use as a drum, or standing waves of the electromagnetic radiation. But in all these cases, you would say that the time evolution is supposed to be very simple. It's just an oscillation, e to the minus I omega t. But the spatial part would be more complicated. It would be determined by the boundary conditions. For example, if you have standing waves of light between two mirrors, then the boundary conditions are important. Or it would be determined by the more detailed position-dependent changes, say for light, the refractive index, or for sound waves, the density, the local density of the medium, and so on. In our case, this particular position dependence will be determined by the potential, of course. And then just like for all these other kinds of waves, there's not only one solution for this, but there are many different solutions of this type. So there's a whole ladder of possible standing waves, and correspondingly a whole ladder of possible values of the energy. And so this is just a typical spectrum that you could obtain if you look for solutions of this kind. If you insert this ansatz into the time-dependent Schrödinger equation, and then you go through 3 lines of math, then you find the so-called time-independent Schrödinger equation. So the Hamiltonian operator, I will comment on it in a moment, applied to phi n would be the energy En times phi n. Now, these are the energy eigenvalues. The corresponding phi n are the eigenvectors or eigenfunctions. And this is math that conceptually, of course, was known for problems in the theory of sound and in the theory of electromagnetism. So when you encounter it in your university studies, maybe for the first time, maybe it's new for you, but the mathematics was well known. So what's this Hamiltonian operator? That's just combining everything on the right-hand side of the Schrödinger equation. So we would say it's the energy expressed as an operator. And in our case, let's keep one dimension, it doesn't matter. The momentum operator is what we already saw, minus I h bar d over dx. Okay. Of course, I hope you know all this more or less, but it doesn't hurt to learn it a little bit again. So these energy eigenvalues, they have the very nice property of being real valued. Otherwise, it would be very difficult to interpret them as energies. This is a consequence of the H having the mathematical property of being a Hermitian operator. So if you think of it as a matrix, it means it's, well, Hermitian. So if you if you flip around the elements in this matrix, if you take the reflection on the diagonal, then you will just complex conjugate the elements. And another consequence of H being Hermitian, beyond the energy eigenvalues being real, is also that the eigenfunctions have a very nice property. Namely, all the eigenfunctions together form a basis, and this basis can be chosen to be orthonormal. So this is very useful. In formal terms, we would say, if I take the scalar product between two of these eigenfunctions, and so how is the scalar product defined? Just to remind everyone, it's the product of these two wave functions, one of them complex conjugated, integrated over all of space. And if they do form an orthonormal basis, and I can always choose them like that if they are energy eigenfunctions, then this scalar product will be 1 if n equals m, because it's normalized to 1, and otherwise it will be 0. So I can write this in terms of a Kronecker delta, 1 for n equals m, 0 otherwise. Okay. And so that is, on this more formal level, what we have here is a scalar product between two vectors in a Hilbert space. Okay, so much for the formalism. I wonder whether there's any question right now. This is, of course, all recap, but it's good to see it once again. And we can draw a few examples if you like. We can have the particle in a box with infinitely high walls. And then, you know, there's this typical way of drawing many different pieces of information in one and the same figure. So this is, of course, the potential. I'm drawing here the potential. At the same time, I can try to draw the different energy levels. So there will be the lowest energy level and the second energy level, which is actually 4 times larger, and so on. And on top of these energy levels, I can draw the wave functions, the energy eigenfunctions. So the lowest eigenfunction, the ground state, is what we just asked in our little online poll. And that's just a sine function, a standing wave. It becomes 0 at the boundaries because there the potential becomes infinitely high, and it would then otherwise cost too much energy. And then the second one is also a sine function, but it has a node, a 0 crossing in the middle, and so on and so on. So you see how it goes. And of course, this is not very amazing. You would find the same mathematics if you consider sound waves on a guitar string. So then here you would have the energy levels, h bar squared kn squared divided by 2m. And this kn is not arbitrary, but these wave numbers or the corresponding wavelengths, they are very special. So L is the size of the box, and so you only have very special discrete allowed values. Okay, so that's particle in a box. You can also have the harmonic oscillator, just to remind everyone of the harmonic oscillator. So again, I can do the same kind of game. I draw the different energy levels. I draw the wave functions. The lowest wave function for the harmonic oscillator, you may remember, is a Gaussian. The second wave function looks also like a Gaussian, but multiplied with a linear function. So it has 1 0 crossing. And then you go on like this, and so on. So these are the energy levels of the harmonic oscillator, and they are really worth remembering because they are so important. So they are h bar times omega. Now this is not an arbitrary omega, but this is the frequency, the resonance frequency of this harmonic oscillator. And then you multiply with n plus 1/2, where n can have the value 0, 1, 2, and so on. And you know, the harmonic oscillator is super important because it has so many applications, especially in quantum field theory. So if you say, I want to describe the electromagnetic field inside a box, or between two mirrors, let's say, these are mirrors, then you would find that the electromagnetic field itself also has standing waves. And now each of these standing waves, even classically, would be described as a harmonic oscillator. And then you go about and say, oh, I should treat this harmonic oscillator quantum mechanically. And you would find that, okay, of course, it has these energy levels. And what then is the meaning in this particular case of this quantum number n? Well, we invent a certain language. We say, if n equals 0, then okay, this is in its ground state. But if n equals 1 or 2 or 3, that means we have placed several quanta of energy inside this particular harmonic oscillator that belongs to this particular standing wave of the electromagnetic field, to this particular mode, as we say. And so if we say there are 3 quanta in this harmonic oscillator that belongs to this electromagnetic mode, then another language says there are 3 photons inside this electromagnetic mode. So suddenly photons, or in other contexts, phonons for sound waves, occur naturally just because you know how to treat the harmonic oscillator quantum mechanically. Okay, so that's particle in a box and harmonic oscillator. And then maybe the most famous potential that started it all, which is just a little bit more complicated to solve, is of course the hydrogen atom, so the Coulomb potential. So again, in this kind of drawing that has many pieces of information, you would draw the attracting potential. So the Coulomb potential is -1/r. That attracts the electron that is negative to the nucleus, which is positive. So it's an attractive potential. And then again, I can draw the energy levels. There will be a lowest energy level belonging to the ground state, and then higher energy levels. And it turns out that for the hydrogen atom and for any potential that looks roughly like this, they get closer and closer together. And there are actually infinitely many here. And above the 0 of energy, there's actually a full continuum. So it's even hard to draw. That's the continuum. So here you can have arbitrary energies, whereas below you only have discrete energies. And again, these discrete energies, they can be given, in this case, they go like some constant energy divided by n squared, and n is 1, 2, 3, and so on. So the ground state would be n equals 1. And this constant for the hydrogen atom is the famous 13.6 electron volt. Okay, so this is a number of the potentials that were discussed very early on. Of course, the solution of the harmonic oscillator is what led Heisenberg on the correct track. And then Schrödinger, also with the Schrödinger equation, was very quickly able to solve the hydrogen atom as well. And so this is where people knew that there is something to this new theory. Because to get the right dispersion relation in free space, maybe, well, there are many ways to do this, but to get the hydrogen atom correct, that's really an achievement. Okay, so far so good, but there's one thing still missing here. Well, there are many pieces still missing, but one thing is that here we always have talked about a single particle. It's a single particle in a box, a single particle in a harmonic oscillator potential, a single particle in a Coulomb potential. But of course, you know that even a helium atom has 2 electrons, and more complex molecules have even more electrons. So what should you do then? And so this is a question: what do you do for many particles? We will come back to that a little bit later when we start slowly discussing interpretation. But the first question you have to ask, if I have 5 particles, does that mean I have 5 individual wave functions? Or how should I approach this problem? And there's a hint already if you look at the Hamiltonian, so either classically or quantum mechanically, doesn't matter. The Hamiltonian always is a function of all the momenta and all the coordinates. So for example, here you add the kinetic energies, but then if you have some interaction between the particles, the interaction energy will actually depend simultaneously on the positions of the 2 particles. And so the question is, what does that mean? Well, it must mean that the types of wave functions this Hamiltonian has to act on, they also have to depend, in this case, on 2 coordinates simultaneously. Anything else would formally not be okay. So immediately we come to the conclusion, if we want to deal with many particles, we have to deal with wave functions that depend simultaneously on all the coordinates. And we will see further arguments for why this is so a little bit later on. This is, of course, also one of the big bottlenecks. If you want to apply quantum mechanics, for example, numerically, if you want to calculate these wave functions on the computer, then even just storing such wave functions that depend simultaneously on many particles is really, really difficult. So that's one of the big bottlenecks. Okay, so much for the formalism. I want to pause here for a moment in case there's already a small question. Otherwise, you have to be patient if you're waiting for the deep interpretation questions, of course, to come up, but I want to pause a bit. Okay, that doesn't seem to be the case right now. Before we move on and talk about the meaning of the wave function, I just want to remind you all that quantum mechanics, the quantum theory that was laid out in 1925, 1926, basically in that form, has had an amazing string of successes. I see a first question. Is there a textbook that goes along with this course? I'm afraid no, not directly. So what I recommend on the website is a set of interesting books and manuscripts, for example, from John Bell, the inventor of Bell's inequalities. There's a very, very nice collection of articles called Speakable and Unspeakable in Quantum Mechanics. But if you want to have something before the foundations part, of course, yeah, then there's many different textbooks of quantum mechanics. Maybe we can defer these discussions then also to the discussion board. Oh, so there's another question. Why do we use minus omega t, not plus omega t? Frankly, no particular good reason. I could, let's see. If at this point I had made the choice that I put a plus sign in front of the omega, then this would have several consequences. This would automatically mean that down here in the equation IH bar dt, I would have needed a minus sign on the left-hand side. So then the Schrödinger equation would look different. It would have a minus sign on the left-hand side. And then forever, every ansatz and so on that follows would have a plus I omega t instead of a minus I omega t. But all the physics that comes out is exactly the same. So I don't know, maybe at some point, having Schrödinger looked out of the window and said, oh, I'd like to have a plus here. Or maybe this is slightly nicer because it's reminiscent of the ansatz for the plane waves that you would choose in Maxwell's equations in electromagnetism. Yeah, so there's no deep reason. You could also develop a quantum mechanics with a plus sign. Okay, so yeah, so Philip Schmidt asked the question, is this so surprising? No, I would say it's not surprising, but it's very important, as we will see also for the foundations of quantum physics, that the wave functions we're dealing with in a many-particle case are functions of all coordinates simultaneously. And that gives rise not only to trouble in the numerics, of course, but also to trouble in the foundations. Someone remarks on the similarity of the Schrödinger equation to the diffusion equation. Yes, it's almost like a diffusion equation, except of course for this interesting little I on the left-hand side. If that weren't there, we would indeed have a diffusion equation, but now we have this I, so we get oscillations instead of diffusion, and that's of course physically very important. Okay. Let me say a little bit about the impressive success of quantum mechanics. So the first study, of course, was the hydrogen atom, and people got exactly the right energy levels, which were already known from Bohr. But then one can also have more complicated atoms, like a helium atom, and so on. And so all of these atoms could now be treated, and you would have something like an electron cloud around the nucleus. And you could also treat molecules, and you would be able to calculate for any particular arrangement of the nuclei, the electron cloud, say the electronic charge density, even in a multi-electron system, at least in principle, conceptually. Now, in practice, of course, this relies on many different, has relied traditionally on many different approximations. And even nowadays, when you have better computers, only for a few electrons can you do things almost exactly. And once you go into more electrons, like for larger molecules, you already have to start doing approximations again. But this means you can treat atoms and you can treat molecules, and you can then also treat, for example, chemical bonds. You can calculate why some chemical bonds are more stable and why are some less stable, and when do they break. And you can extend this to solids. For example, you can have a crystal lattice, and you can calculate the binding energy of this crystal, and you can calculate other things like, for example, the colors of materials. So the colors are, of course, a function of the possible energy levels inside, let's say, this molecule, because in order for light to be scattered, what you want to have is that you have two energy levels, let's call them E0 and E1 of the molecule. And as the photon comes in, it precisely matches the transition between the two energy levels, and then it will be absorbed and it will be re-emitted, but into different directions. So you will see that as a color of the material that is made up out of these molecules. So for the first time ever, one could understand the color of materials, absorption, emission, heat, radiation, and so on. And then you can go further. You can ask about electrical conductivity. So classically, it's quite surprising if you have, let's say, here are the, let's say, here are all the atoms inside your material. And now you have a little electron that wants to pass through this material, an extra electron, let's say. And what would happen classically is you would expect it to bounce off the atoms and then have a very funny bouncing trajectory and very quickly lose its initial velocity. And so there would be a tremendous electrical resistance in every material. But in fact, this doesn't happen. What really happens is that the single electron is actually, as a matter wave, is like a plane wave extended across a larger portion of the crystal. And this plane wave moves completely without scattering through the crystal. And it will scatter only if there's a defect. For example, if there's an atom missing or so, then it will finally scatter. So for the first time, one could understand electrical conductivity. And of course, similarly, one could understand other effects like magnetism. So what really leads to the tiny magnetic moments in materials to align themselves with each other? And the fact is that this is due to Coulomb interaction and Pauli principle. So things that were completely unknown before, or their relation to magnetism was completely not anticipated before quantum theory came along. Yeah. Likewise, the mechanical properties of crystals, light quanta, of course, we already discussed. You can also zoom in. You can look at the nuclear structure. Nuclei are, of course, much smaller, and they consist of different elementary particles, neutrons and protons. They are really tiny. But you can apply the same kind of quantum mechanics. There's nothing new there conceptually. You can even zoom in even further and invent more advanced theories like quantum chromodynamics and so on. And still it's the same quantum mechanics that applies. And together with that, you can then describe the physical effects like radioactivity, fission or fusion, and other elementary particles. It's all the same quantum mechanics. So in some sense, it's all the same modest Schrödinger equation that can be applied to predict all of these different things. There never occurs something that is suddenly conceptually extremely different. So these are all the physical systems that could be understood using the new quantum theory. And then there's also many different applications that people were able to partially understand and partially even predict and make happen for the first time. So you all know of lasers, of course. This is a result of the quantum theory analysis of what goes on inside an atom. When the atom is already excited, another photon comes along, and then in the end you have induced emission and you emit two photons. There are superconductors and superfluids where you can explain that the electrical resistance can drop to exactly zero at low temperatures. There's applications like nuclear and electron spin magnetic resonance, like used in medicine. There are semiconductors, the whole semiconductor industry with the chips-based, with the electronics based on semiconductor chips, also relies on quantum mechanics. And who knows, maybe in the future there will be superconductors at room temperature. Maybe there will be quantum computers. And all of these things would be very impossible without the help of quantum theory to back it up. Yeah? So these things would not have been discovered by accident without knowing quantum mechanics. Okay. So I would say it's fair to say that about 2/3 of physics research nowadays rely on quantum mechanics. Yes, thank you. Someone remarked, right, there are already superconductors at room temperature. Of course, these are at very, very high pressures. So maybe for applications, that's not yet the ultimate goal, but it's very interesting because it will produce better understanding. And once we have better understanding, we can also maybe tweak it around a little bit in order to go to room temperature and normal pressures. Okay, so let me go on. once you have learned all of these things in your first course of quantum mechanics, or maybe while you're learning things, you start wondering, what is the meaning of the wave function? And of course, this is a big question, and in some sense, we will spend the rest of this lecture series trying to figure out the meaning of the wave function. But let's just start with it in a little bit modest way. So one of the things when you encounter such a new unknown wave field is, of course, you want to compare it with other wave fields. So, for example, you could compare it to sound waves. And we know how sound waves work. For example, if you have sound waves in a gas, you have the gas molecules less dense in some regions of space and then more dense in other regions of space. And again, less dense, more dense, and so on. So there are regions with high and low pressure and high and low density. So I could draw, for example, the density as a function of position, and this is what I would get. And then the waves are waves of pressure or density. Or you could have elastic waves or surface waves. For example, if you have all your atoms inside a crystal lattice, so these are the atoms, then in order to describe a perturbation where these atoms are being moved around a little bit, you would introduce what is called often a displacement field. So it tells you how much the atoms have been displaced, and then the waves that we're talking about are waves of this displacement field. And if I have water, if this is a water wave, then I would also introduce a field, for example, that describes what is the height of the water wave as compared to some normal height level. And I could call this, well, h is maybe a little bit problematic, but h of x and t. And so I would describe water waves. And in all these cases, the physical meaning of the waves is very, very obvious. Now let's turn to electromagnetic waves. What are these waves of? Well, these are waves of the electric field and the magnetic field. Now, how physical are these fields? Well, they are pretty physical, I would say, because at least there's a way to measure them. So you could take a charge. The charge also moves at some velocity. And then you measure the force that is produced on this charge. And you will find out that this force has a component that does not depend on velocity. That's presumably due to the electric field. So it allows you to measure the electric field. And another component that is proportional to the velocity. That's the component due to the magnetic field. So that allows you to measure both. The problem is a little bit, you get into trouble with the interpretation of E and B once you ask yourself, well, what exactly is moving? I know that for sound waves, it's the density that is changing. I know that for elastic waves, the atoms in the crystal are moving, for the water likewise. But what is moving here? What is the medium in which these waves move? And then at first you give a name to this medium, which is the ether. But then you figure out, no, this would contradict very important experiments. And so that leads you step by step to the theory of special relativity. And then you recognize that everything depends on the reference frame. So what is an electric field and purely an electric field for one observer could be a mixture of both an electric field and a magnetic field for another observer. So there already the E and B, at least individually, lose a little bit their meaning, and suddenly their definition becomes reference frame dependent. So things are not quite as nice, I would say, as for the elastic waves or for the sound waves. So we start to have a situation already there for electromagnetic waves where you could feel a little bit uneasy, and at least 100 years ago people felt uneasy, but maybe not very much anymore. Okay, so now coming back to the wave function psi, what is the sense, or what is the meaning that we can attach to the wave function psi? And for the moment, well, let's say we don't know at this stage of the discussion, but we can at least look at a few general aspects, and from these general aspects, maybe we understand a little bit more what's going on. So the first interesting aspect is that there is a conserved density. So we have a linear wave equation. So in general, if there are conservation laws, then we expect them on formal grounds to be quadratic in the field. One such example would be the, say, energy density in the electromagnetic field, or even the momentum density in the electromagnetic field. All these are quadratic in the fields. And what we would like to find is conservation laws of the following sort, local conservation laws. So typically they look like this. You have some density. We do not at this moment yet say which density. Some density that can be expressed through the field and is presumably quadratic in the field. And if you take its time derivative, you find that it always can be expressed as the divergence of some current density, which again is a function of the fields. And so then you have this so-called equation of continuity. And it will depend on the particular wave equation. What are these densities and current densities? And there may be even several choices. So again, for the electromagnetic field, you can play this game for the energy density, if you like. Now the claim is that for the Schrödinger equation, we do have such a conserved density equation, such a continuity equation. And for the Schrödinger equation, of course, you all know what this density is. Namely, we have rho equals psi squared. So that's, of course, a function of both of the position, possibly also of the time. And so that's a conserved quantity, or rather conserved density. So if you integrate it over all of space, then this integral will not change. And what is the corresponding current density? They always come in pairs, conserved density and current density. Well, the current density that you need in order to fulfill the continuity equation is again quadratic in the field, and it has this shape. So there's psi star and psi, and in between we have basically the momentum operator divided by m, so that would be a velocity. And in total, this could still be a complex quantity. So actually, what we need to take is the real part of this. So that would be the velocity operator. And it turns out if you plug everything in and use the Schrödinger equation, you will find that this is conserved. Now, why? So apart from the formal aspects, why do you think it makes sense? We can have a short look at hydrodynamics. It's always good to connect different fields of physics, you know, because then you can learn more and make analogies. So hydrodynamics means, okay, I have, let's say, a lot of atoms that make up my fluid, and they flow along. These are the streamlines of the fluid flow. And again, of course, the mass density must be conserved. No particles get lost. So we already know what is rho. Rho is the mass density, or the particle density, particles per volume. The question is, what is the corresponding J? And it turns out once I tell you the velocity field, the J is simply rho times the velocity field. So how much density is there and how fast is it transported? Multiplying them together, you get the current density. And you now see that something rather similar, if you don't look too closely, also is happening for the Schrödinger equation, because you see psi star times psi, that's something like psi squared, that's the density. And then in here, there's the velocity. So luckily, it's also something like rho times v. So everything kind of makes sense. What is interesting about this conserved density is that it's independent of at least the potential. Yeah. So you can have an arbitrary potential. This will always be true. The forces will be different. The wave function will evolve differently. The density will stream differently. But at least these two expressions for rho and for J, they will remain the same. So now this is a very important insight, you see, because it may give us a hint as to what psi means. Oh, can any other form of J still satisfy the continuity equation? Well, as always, if you take the J here and add some divergence-less vector field, then obviously it would still fulfill the equation of continuity. But what we want to have somehow in addition is, of course, that there is a simple relation between the J and the underlying field, in this case, the psi. So there is a little bit of ambiguity that is true, but if you want to have this nice relation between J and psi, then you don't have much ambiguity. Okay. The same ambiguity also, that's not something special about the Schrödinger equation. The same ambiguity happens whenever you have such a continuity equation that you can add another divergence vector field. Okay, so now have we learned something is the question. We now have a conserved density, that's nice, but what is the meaning of this density? And so the first guess is due to Schrödinger. Because you know, if you look at what happens in the hydrogen atom with a nucleus, and then you calculate the ground state wave function, let's say, what you find is that the psi squared of this ground state wave function is somehow concentrated around the nucleus. So maybe I can draw it like this. So it gets more and more dense near the nucleus. And it turns out that since psi squared is normalized, so the integral over psi squared is 1, you can interpret this as the charge density. So the individual charge of an electron times psi squared would be a charge density. And thus gives a lot of correct insights and results. And even nowadays, when people, for example, quantum chemists discuss molecules, they will have this picture in their mind of the charge density of the electron cloud, and it will be calculated like this, or maybe you add up the charge densities of several electrons or have slight modifications, but that's basically it. Now the question is, however, if we want to fundamentally take it as the charge density, is the electron then smeared out? That's the question. And initially, Schrödinger really thought that this could be the case. And it would not be a contradiction at first sight, because all these dimensions are so small. We are talking about 10 to the minus 10 meter. So it might very well be that particles on this small length scale are smeared out a little bit. But there are experiments that directly contradict this very naive interpretation. First of all, we could then ask the question, okay, should then different parts of this negative cloud repel each other? And if so, why don't we see this happening in the Schrödinger equation? That would be a first question. But also, there are experiments where definitely the wave can become extended. And so let's draw this. If I have some obstacle here, and then I have a wave coming in. Okay, so this is a wave packet. These are the wave fronts, the lines of constant phase. And it's moving like this. And so this is before it has hit the obstacle. And the question is, what happens afterwards? And so again, I have my little obstacle. And it turns out what happens afterwards is, of course, this wave is scattered into all possible different directions. Maybe it even has an interesting directional dependence because of interference effects and so on. But it really goes into all different directions. And so likewise, the charge density gets very distributed. So we could easily have a situation where maybe this is, I don't know, could be a nanometer or something, so microscopic, and later end up with a situation where this could be extended on the macroscopic scale by a meter. And then we really run into trouble, you see, with this smeared out electron interpretation, because that is definitely not what is observed in the experiment. You could literally measure this with apparatuses that are able to measure the effects of the electric field generated by such a smeared out charge density on other charged particles. And you don't observe smeared out electrons, not on this length scale. And so this is not just a Gedanken experiment, the scattering experiment. These are, of course, being done. Electrons are being scattered off of atoms. And the first one to analyze this particular kind of experiment was Max Born. So the experiments in question, so this is an atom, and this is an electron. These are the so-called Frank-Hertz experiments. And they are quite interesting because if the electron is fast enough, it can then also excite the atom and transfer part of its energy to the atom. And you see then discretized energy transfers because the energy levels of the atom are discretized. But if you want to do the theoretical calculation, of course, you exactly end up with such a situation where the psi squared is distributed over all of space. And so that led Max Born to come up with a new interpretation, because he analyzed these scattering experiments and he found the charge density thing doesn't work, but maybe the psi squared has the meaning of a probability density. So famously, he first was of the opinion that maybe psi itself is the probability density, because in some parts of his calculation, he was still working with real valued wave functions, and maybe it could have been, but even then, if it becomes negative, it's not so nice. And anyway, in general, the psi is complex valued, so that doesn't work. So he figured out quickly that psi squared should be the probability density, also because we know that it is conserved. And so what this psi squared really means is that as for any classical probability density would say that the if you take it at some point and then you square it, that's a probability density. So that means if you multiply by the volume around this point, then you get the probability to find your particle, for example, your electron, inside inside this little volume element. So this is R, and this is the volume, the volume. And so this would be the probability to find the electron in a good measurement inside this volume. Of course, it scales linearly in the volume. If you make the volume twice as large, you are also likely with twice as high probability to find the electron inside this twice larger volume. But that's what this means. Okay, so that's great. And that also means that suddenly we have a nice interpretation for our equation of continuity, because that becomes nothing but the conservation of probability. So it's the local conservation law. And if you integrate it over all of space, so to speak, the probability itself would always be obtained by integrating rho over space. And if you integrate it over all of space, if you start with 1, it will always remain 1 at all times, because you see, if you take the derivative with respect to time, then of course you have something like this. And then you can use Stokes' theorem, but if you take a surface of your volume that goes to infinity, where you don't have any psi anymore, then you get 0. Sorry, not Stokes, Gauss. Okay, so that's great. In what cases can probability be negative? Never. So if it has the meaning of a probability, then it can never be negative. Sometimes people introduce formal definitions that have many of the properties of a probability, but that can sometimes become negative. But then you should not use the word probability, and people call this quasi-probability. So even in quantum mechanics, this can occur, but then you need to think very closely of what does it mean. Here, this is always positive, no problem. Okay, so that was the great idea of Max Born back in 1926, for which he also got the Nobel Prize later. And this is the insight that has stood the test of time. So there has been no experiment or no further theoretical development that has made it necessary to change this insight. What about the meaning of J? The meaning of J is, of course, it's the probability density current. So in case, for example, if you consider a situation where your wave is really propagating essentially in one direction, you can calculate the momentum, but also the velocity of this wave packet, let's say. And then at each point here in space, you will have a J, which is simply psi squared times v. So it's very simple. It tells you how much probability, if you were to draw a little surface, and you ask yourself how much probability goes through the surface per time, then that would just be J times the area of this surface. Okay, there's another question about the Wigner function. I would try to defer this to later. It has no meaning right now in our discussion, and the Wigner function is just an abstract invention, whereas this psi squared, that is the real probability density. Okay, good. So now I just want to make the point that this is even much more general. in general, we would have, now coming to a slightly more abstract formulation, we would have the time evolution of a wave function understood as an abstract vector in Hilbert space. You probably know that you can introduce a time evolution operator, which when it acts on the initial wave function gives you the wave function at a later time. This time evolution operator is unitary, which means if you take its summation conjugate, it's actually the inverse. And so what this means is, if I take the scalar product of psi with itself, which you remember, if I write it explicitly as an integral, is just psi of x and t squared dx integrated over all of space. Then I can also write this as u of t times psi 0, u of t times psi 0. Now, because I know how to treat Hermitian conjugation inside a scalar product, I find this is the same as u dagger of t, u of t, psi of 0. And now u dagger is the same as the inverse of u, so the whole thing is just 1. So I get the scalar product that I had in the beginning of time. And so the total probability is conserved, which is very nice. Okay, so far so good. Let me end then today. We are already coming close to the end of today's lecture, by asking ourselves, well, in 1926, when this concept was introduced, how radical was this idea of a statistical interpretation? What statistical ideas were there before this point in time? And actually there was the whole of statistical mechanics. So think of particles in a gas flying around with random velocities, Maxwell-Boltzmann distribution, that was already there. There was the Boltzmann distribution, for example, if you have particles in a potential, then the density of these particles or the probability density to find a given particle at some position would be given by e to the minus potential divided by kVt. So all of this was around. Then, of course, there was, so this is basically Maxwell-Boltzmann. Yeah. Then there was also already radioactive decay. So it was very clear that this was a stochastic process. You could give a half-life. You could say when, statistically speaking, things would decay, but you couldn't predict it precisely. So again, there's statistics there. And both of these things had been observed, even not only averaged over many, many billions of particles, but even individually. So for the Boltzmann distribution, of course, people were not at the time able to observe individual atoms, but you could observe slightly larger particles, and then they are bombarded by all the little particles in a gas or in a liquid. And then you would have Brownian motion, and Brownian motion had been observed already. And it was observed to have exactly the characteristics of this random walk that you would expect from this picture of the bombardment of small particles. So that was observed under the microscope. And radioactive decay, since each decay is quite a drastic event, and you can very easily detect with a Geiger counter the individual decay event. Also there you had really a measure of individual events. So you would have click, 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 click. So this was all known at the time. Then there were, of course, cloud and bubble chambers for high energy particles. So they all showed individual events, but it has to be said that they did not show quantum interference. Yeah? So there was decay, but there wasn't never at this time any simultaneous observation of both quantum interference patterns and individual statistical events. This was not yet there. So for quantum mechanics, only ensemble measurements of many, many billions of particles were known. Today, of course, the situation is very different. So today we have amazing photon detectors that can detect photons with significantly more than 90% probability. So if you have a photon, you are quite sure that you catch it. And there are even CCD cameras which have single photon resolution where you can detect individual photons arriving on the camera. There are likewise single electron detectors. So a single electron is enough to set off avalanche of other electrons, and then you measure this event. And we can also detect single atoms and ions. So we can detect single quantum events, and then we really see the statistical nature. And when there are many such events, we can then do statistics and test whether the predictions for the probabilities are actually fulfilled, and it comes out right in every single case. So I think that's probably enough for today's lecture. I want to pause for a moment, whether there are any extra questions about the things that we have been discussing in the last few slides. And then I will tell you briefly what we will do next time. Are there any questions? So at the moment, I don't see any. Okay, so this is so here's a question, but maybe not quite serious. What's your take on the many worlds interpretation? Well, this is something that we will discuss as the lecture series goes on, because right now, if I answer in one sentence, that will not do justice to it. But thank you for asking and setting up everyone for what will come in the lecture series. So here's a quick preview then of what we will discuss next time. We will say something about the so-called collapse of the wave function. We then want to try to understand what happens really at the level of single particles. We cannot give definite answers, but we slowly inch towards these fundamental questions that are then the subject of the rest of this lecture series. We will say something about the Heisenberg microscope. And then we are already set up to start discussing Bell's inequalities. And so that should be very interesting. There's another question. Something was said about probability predictions from these experiments. Well, the point is, if you have only individual events, of course, then in an experiment you only see, oh, there is an event or there isn't. In order to test the predictions of quantum mechanics, you need to take many events. For example, you need to count, if I want to take this particular example, you need to take a larger time interval and you need to count how many events. And then you compare that against the prediction that quantum mechanics would have given you for the number of events within this sort of time interval. And if the number of events is large enough, then the statistical fluctuations will be relatively small as compared to the average. And it is the average number of events in this case that you would compare against the predictions of quantum mechanics. So quantum mechanics will never make a prediction on the individual event. It cannot tell you, oh, now you should expect the photon, but it will make predictions about average quantities, about probabilities. Okay, someone wants me to quickly discuss again the dispersion relation for the matter waves. Sure. Let's see, where do we have this? Okay, so, well, you know, we have these two relations between energy and frequency and momentum and wave vector, which we take as our starting point. That's a hypothesis. We know this hypothesis is nicely consistent with what was found for photons, but then it is just a hypothesis at this point. We also know the relation between energy and momentum, simply from classical mechanics. Energy is p squared over 2m. And then just by inserting E equals h by omega, P equals h by k into this equation, we immediately get the relation between frequency and momentum. So this relation, and that's the one that I draw here. So this is the starting point. This is what you want to get. You could also try to do it for the relativistic dispersion relation. Actually, that's what de Broglie wrote down. And this is also what people tried to first develop a wave equation for. This led them to what is now known as the Klein-Gordon equation. Mathematically, it even looks, I would say, even simpler than the Schrödinger equation. It has a second time derivative and second space derivative. So it's very nicely symmetric, very beautiful. But the problem is that then the interpretation was even more difficult than for the Schrödinger equation. And only later it was understood in the context of quantum field theory how you should interpret these things. So this was, so to speak, a little bit too ambitious to go immediately to the relativistic case. But of course, you cannot know in advance. So Mr. Klein and Mr. Gordon, they had a good reason to try this first, because relativistic mechanics is the more fundamental theory. Okay, are there any other questions? The recording of each presentation should be posted basically after we finish this, then it will be still converted. And if I don't forget to upload it, it will be up there tomorrow. Okay. So I think all the other extra questions of also what could we cover, maybe we can discuss this as we go along in this lecture series. Again, I want to point you not only to the website, but also to the discussion group. So if you have some particular special questions, maybe the discussion group is also a good place to start. Well, and with that, thank you everyone for staying around. See you next time. It was a pleasure to have you here. And ciao. See you next time.